So now let's talk about semantic segmentation. So what is semantic segmentation? It's a process that assigns a label to each point in a point cloud, allowing machines to see and understand complex environments. Unlike images, point clouds are unstructured, unordered, and sparse, which makes segmentation a unique challenge. In this work, we analyze how a lightweight model, PointNet, handles these issues in both scientific and real-world scenarios. There are several models for point cloud segmentation. PointNet was the first to process each point independently and use max pooling to get the global feature. Then PointNet++ came and added local information by looking at neighborhoods. More recent models like KPConv and transformer-based ones, such as OneFormer, are more accurate, but they need a lot more memory and are way harder to train. So why did we choose PointNet? We choose PointNet because it's simple and doesn't require much hardware. Each point goes through a shared layers to extract features. Then a max pooling layer summarizes everything into one global feature. We add this global information back to each point and use another MLP to predict the label for each one. The main limitation is that PointNet doesn't really capture local details or spatial relationships very well.
So our main goal in this work was to compare the difference in performance of the neural network in two different datasets. ShapeNet part, which is this synthetic dataset, which has like really nice point clouds, as you can see, and Toronto 3D, which is an outdoor dataset that has like more noisy point clouds, which are like can be more dense and stuff like that. So we had to adapt the code of PointNet to, be able to train it using this dataset and this dataset as well, because the code that was available didn't work with this one. So yeah, we did it and we compared the results. And pretty much what happened was like the results in this dataset were pretty good in ShapeNet part because the PointNet deals better with it because it has less noise and you don't need a hierarchical architecture to like extract features in a great way and segment it the right way. And Toronto 3D was really harder. So to conclude, there are a few important takeaways we think we can get from our experiments. First, hierarchical architecture seems to be more suitable for this type of test. Models like PointNet, which lack hierarchical architecture, tend to struggle with complex and dense point clouds like the ones shown in Toronto 3D dataset. In addition to this, we highlight that point clouds can be really hard to process, and it can take a lot of computational power to segment it using machine learning models or even simpler strategies.